Good afternoon and welcome to Advanced NMR Spectroscopy course. So today I'll start talking about the NMR machine and how to record NMR spectrum in a NMR machine. This part will be very useful when you go for learning 2D NMR and beyond that. So I've shown here the major components of a NMR instrument. The one is your magnet system, okay, the superconducting magnet system, and then another component is the console, and the third component is the computer. So this magnet is the heart of the NMR machine. Everything happens here, which is done by the console and which is commanded by the computer. Okay, so in the magnet system, there is a powerful magnetic field which is ranging from 5 to 20 Tesla, depending on the machine, are produced from a superconducting magnet system, and then samples are placed within this magnetic field and exposed to radio wave pulses. Okay, so in this, the major component is your magnet system, and you have the probe head where the NMR spectra or the radio frequency pulses are given, and also the signals are received. This console actually does, it is the major component which actually transmits the radio frequency and also receive the signals, and everything is commanded by the computer. So it has radio frequency synthesizer, it has amplifiers, it has analog to digital converters, then it has the log system and also SIM system. And so these things are normally not being touched by a normal during normal operation of the NMR spectrometer. It is mostly everything is done using this computer. It is starting from instrument control to data processing. So here I have shown that a magnet. So superconducting magnetic coil is placed in the liquid helium bath. You can see that there is a big dewar. So the outer component is having liquid nitrogen. Then inner dewar is liquid helium, and inside that liquid helium, the superconducting magnetic coil is immersed. You can see, which I have shown it here. This is the superconducting magnetic coil. And then as I told you, the helium dewar is surrounded by liquid nitrogen dewar, so that the loss of helium will be minimum. So beside the main magnetic superconducting magnetic coil, there is also cryo SIM coils. You can see these are the cryo SIM coils. These are the cryo SIMs for these, and these are so these are also placed inside the liquid helium chamber. So these SIM coils actually brings a if there is most of the homogeneity in the magnetic field from the main magnet. So if there is any inhomogeneity, so that has been taken care of by these cryo coils, and these cryo coils are actually sealed during the installation. So this is not done by regular operation. Okay, so once the magnet is installed, at that time only the engineers they fix all these things, and so it is not regularly used in the operation, during operation. Okay, so there are also beside this, so you have the main magnet, then the cryo SIMs, and then there are also room temperature probe SIM coils. Okay, so these are one which are placed, okay, inside the inner surface. Okay, so and they are at room temperature. As I mentioned, they are room temperature probe SIM coils. Okay, and these SIM coils have to be adjusted during regular operation. We will speak more about these things later on. And then the NMR sample tube containing the NMR sample solution in a solvent, mostly in a deuterated solvent, is placed. You can see this is the NMR tube, which is placed inside a rotor turbine. So this is the rotor turbine. Inside that, the NMR tube is placed, and that is put lower through this. This is your room temperature seam tube, through which the sample is lowered, and this is your probe, and this sits. The sample volume comes at the probe head, where all these coils are there. Okay, so both the radio frequency as well as the signals generated are then obtained from this part of the NMR tube, or the volume where the sample is there. And also this rotor turbine can be spin, okay, depending on what spin rate you want. It can be varies from normally it is spin between 50 to 100 hertz. Okay, and then the signals which come from the magnet is then processed electronically. We'll see those things later. So these I have shown here with how a NMR sample tube looks like. You can see they are uniformly diameter tube, glass tube with uniform thickness, and also these glass are very special glass. They are made in such a way so there is no paramagnetic material in these glass tubes. Okay, otherwise it will disturb the magnetic field. And then you dissolve the sample and put inside your NMR tube, and then you put it through a rotor turbine, and there is a measuring device. So you have to put this thing in that measuring device before you put into the NMR machine. Otherwise the tube will hit something inside and it will break, or there may be inappropriate position, so that the volume of the sample may not be filling the magnetic field. So ultimately, see, this is the way when the NMR tube sits into the resonance cavity. You can see that only this small volume of the sample sees the so this is in the magnetic field, but this is the sample cavity where all your radio frequency pulses or radio frequency source is located, or as well as detecting coils are also located. Normally this tube diameter is around 5 millimeter, and the thickness is around 0.8 millimeter, and you can see that the solvent height is around total height of the solvent will be around 2.5 centimeter. If you put more volume also, there is some issues comes, and if you put less volume also, there will be issues of seaming. We'll see that thing later on. Okay, so now most important thing is the probe head. Actually, probe head is a mechanical component which can be changed depending on which nuclei you would like to observe. Okay, so sometimes if you just want to see proton, you will be putting a proton probe, or if you want to record a proton and carbon, you can put a proton carbon dual probe like that. Okay, or if you want to record many nuclei, you can use a multi probe. Okay, so this is actually placed inside the seam tube, which is at room temperature from the bottom of the NMR instrument, and this is nothing. You have a liquid nitrogen dewar in the liquid helium dewar, and this is your main superconducting magnetic coil, which is producing the magnetic field, and inside this seam room temperature seam tube there are the seam coils. Okay, you can see it has been expanded, this part where the sample is there. You can see there is a spinner. Okay, so that spinner is sitting on a particular position, and you can see this your transmitter and receiver coils, and then this is called a resonance circuit. You get the signals, and then the signal goes to the preamplifier. Okay, so the probe head, as I told you, it contains the receiver transmitter coil. So this is the receiver transmitter coil, and normally it is the single coil. So that coil actually gives you the pulse, and again the same coil is used as a detector, collects the signal. Okay, so normally this is the setup being used. In fact, in most of the time you'll see there will be two coil sets. Okay, one will be inner coil. So always with that inner coil will be tuned to deuterium. We'll tell that why we are talking about deuterium lock. We'll speak more on this. So inner coil will be tuned to deuterium log and a second frequency. Second frequency will be used for your depending on what type of nuclei you would like to detect. And then you will have a outer coil also that can be tuned to third and fourth frequency. Like you will see that when you record a carbon-13 proton decoupled, you will see the proton the proton frequency is frequency is tuned in the outer coil. Okay, so the inner coil is more sensitive. Okay, more sensitive means it has a better higher signal to noise ratio and gives a very short pulse length. Okay, so sometimes people use the inverse carbon probe. Okay, so there are normal carbon probe and inverse carbon probe. So in inverse carbon probe, when you detect, you will have the proton in the inner coil, and outer coil you will have the carbon-13. So that's why you will see that is used with very high proton sensitivity, and you will see this is used for many proton carbon correlation experiments. And there are also carbon dual probe, which has the inner coil is tuned to deuterium and carbon-13. Like deuterium will be always there in the inner coil, and also the second frequency is carbon-13, and the outer coil will have dedicated to proton frequency. Okay, so because that will be used for proton decoupling. We'll talk more about proton decoupling later. Okay, and then this resonance circuit, which contains the capacitor. Okay, this has to be tuned. See, if you are using the same solvent, let us say CDCl3, so you need not to bother. But if you change the solvent, then you have to tune this resonance circuit so that the deuterium, because see, when you put a different solvent like acetone D6, that will have a different resonance frequency than the deuterium in chloroform. So that's why this resonance circuit has to be tuned to the deuterium frequency. So you have to tune that. And this probe head is connected to the preamplifier. So whatever signals, these NMR signals are very weak actually. So they will be pre-amplified. This will be very close to the magnet, and then it will be further amplified and detected. Okay, so the now in the console you will see there are the radio frequency source. So these radio frequency sources are electronic components. They produce sine and cosine waves at appropriate frequency, and normally the frequency resolution is better than 0.1 hertz. So that means you get a very good resolution. And then there will be amplifiers, so they boost the outgoing and both outgoing and incoming signals, the radio frequency signals. So whatever radio frequency generated, it boosted to high power and it goes to the so the boosting or the B1 field strength is actually controlled by these amplifiers. Okay, similarly when the signal is received, they are also amplified. And then since analog to digital converter is that the signal, whatever initially you recorded, that is in the analog form. But if you want to do the Fourier transform, because that is the we'll be using, then Fourier transform, you have to bring this analog form into a digital form. Okay, so normally these 16 to 18 bit digitizers are used for this purpose, and I think all of you know that. And then the computer is normally a Unix machine, which is having a large amount of RAM. Okay, and then you can have additional PCs also, which can be used for processing of the data. Now let us see about the SIM system. So I have told you that there are two types of SIM coils. And the role of the SIM coils are that they correct locally slightly different magnetic fields, okay, by passing small amount of currents, because they are small. Actually, there are also small magnets, electromagnets. So if you pass them small currents, they also produce locally magnetic field, and by this way they bring homogeneity to the main magnetic field. So the cryosims, I have already told you, they are installed inside the liquid helium temperature and used to correct the inhomogeneous field created by the main field. Okay, but that is not done regularly. It is done once when the machine is installed. The room temperature SIM system brings down any inhomogeneity of field after the sample is placed. So once you put the sample, there will be inhomogeneity. Okay, so that is regulated by this SIM coil, and that you have to do it during the operation of the machine. Okay, so the room temperature SIM, there are two groups of SIMs, room temperature. One group is called on-axis SIMs. So they change the field, they correct the field homogeneity along the direction of the magnetic field, and another are the off-axis SIMs, like they are not the along the axis, like along the axis like x, y, then xy, x square minus y square. Okay, and most of the time you have to adjust these Z SIMs, means along the axis. These SIMs, there may be some adjustment required, but not rigorously. So see this, if you don't adjust the SIM properly, then you will see that affects the quality of NMR spectra. So suppose if your SIM system is correct, or it tells about the overall homogeneity of the magnetic field, you will see a very beautiful Lorentzian peak shape. Okay, but if the fields are not uniform, suppose if this Z and ZQ SIMs are not proper, you will see that still it is there is a lot of broadening of the peak starting from the base to the top. Okay, similarly if you have the Z4 SIM is not proper, you see there is a quite broad baseline. Similarly, if your xy and x square y square minus is not properly seen, you will get a sharp line, but you see that you have a lot of satellite peaks. That is, so that will actually now confuse with probably you will think that these are coming from some other nuclei. Okay, similarly the Z square, if you see the Z square SIM is not done properly, you see this is a huge base broadening at the base. Similarly for X, Y and other SIMs, you can see there are side bands. Okay, now we'll go for the log system. See, normally if you see when even it is the magnet is kept inside the liquid helium, but there will be always some drifting of the magnetic field. So what do you mean by drifting? Means if there is a slight change in magnetic field, your resonance frequency will change. So if there is any change in resonance frequency, but very little change in resonance frequency, so that will lead to the line broadening. Okay, so how to avoid this? Okay, so so what you have to do, so that you have to keep the magnetic field stable. Okay, and that is achieved by locking at deuterium frequency. Now we'll tell about how. So deuterium log, what it does actually, deuterium log measures the frequency of the deuterium nuclei of the solvent. Okay, so whatever solvent you have added, so it always monitors the frequency of the deuterium nuclei. Okay, so this system has a feedback loop. Okay, so as the deuterium of a particular solvent, deuterium has a particular frequency. Okay, so your transmitter frequency is set to that frequency. Now if there is any change in the magnetic field, so there will be change in the deuterium frequency. Okay, because it will not resonate that. So that will be automatically what it will, there will be a Z0 SIM coil. Okay, so that coil will now either pass some current. So in depending on the direction, it will add to that to bring make the field homogeneous, or the constant value B0. Either it will increase the field or decrease the field. By both the way, it will maintain the field constant. So that's why it is a feedback loop. So once the deuterium frequency, so at this point we will call the magnet is locked. That means the deuterium frequency is locked and the field is homogeneous for that particular frequency. Okay, so once the deuterium frequency is locked or kept constant, so automatically all other resonance frequency also kept constant. There will not be any change. So that is the advantage of locking. If you don't lock, there will be a broadening of the signal. This is a very important thing that you need to lock the NMR machine. The next important component of the NMR spectrometer is the transmitter and receiver system. Transmitter and receiver system means transmitter gives you the radio frequency pulse, okay, and receiver also it receives the NMR signals. Okay, so but if you see the NMR, we are using a megahertz or a radio frequency, so they come in megahertz. Okay, but if you see the electronic component, they are more convenient to handle the audio frequencies. That means they are in kilohertz than handling radio frequency. So let us see how this thing is done, so that the electronics, actually most of the electronic component handle only the audio frequencies, or in the frequencies in the range of hertz to kilohertz. Okay, we already know that the B1 field, the radio frequency field rotates about the B0, the applied magnetic field, with frequency called carrier frequency, or called transmitter frequency and rotating frame frequency, which is the central frequency of your spectrum. It will be always set to your central position of your spectrum. Okay, or very close to that. Okay, similarly, you will see the received signal. So your that is actually comes as a megahertz, but it is also transformed down to audio frequency, so that I told you further processing or further handling will be much easier. We will see that how it is being done in next few slides. It will come. So let us see how it detects. So if you see the normally we have told that the B1 is applied along the X prime axis in the rotating frame, and this is the applied magnetic field, and you have the net magnetization, and your detector is along the y-axis. Okay, so let us say if you give now a 90-degree pulse. Okay, you give a 90-degree pulse. Okay, so what it does, it brings the magnetization, this M, into the y-axis where the detector is placed, so it sends a signal. Okay, so you get a current or voltage here, and then you see, now let us see, this is processing in as I told you that in the rotating frame we detect the signal as offsets. So if this is on resonance pulse, you will see the M is not moving anywhere. It will slowly decay, magnitude will decay along the y-axis only. Okay, due to the T1 and T2 relaxation. But let us say you have your the M is having offset, a negative offset I have shown here. So automatically, if it is in negative offset after the B1 pulse, as the time increases, you will see that it is rotating in the anti-clockwise direction. That only you see. So automatically you will see the initially this is your 0 time, you have a signal because your detector is here. Now as it is moving away, the signal, you see, when this is here, when it is there, you get the full signal, but when it is here, your projection in the your projection along the y-axis will give you this will be the magnitude of your magnetization. So the slowly as it is moving fast, so at this point your intensity of signal is 0, because it is along the minus x-axis, and then you will see that it will now become negative. Okay, because this is in the this is in the minus y, so this will be projected to minus y. Okay, so you will get a negative signal. So as the time, so and then you will keep on doing this. Okay, but if you see in the same thing, suppose if the this is your a negative offset, suppose if it is a positive offset, so this the same magnet, let us say this is a positive offset. Okay, same they have the same value, then also you will see the same signal. It will be when it is at y-axis, you get this thing, then as it is rotating in clockwise, you see that it will decrease, then when it will come to here, it will be 0, and then when go this side, you will have the negative y. Okay, so what I mean to say, that the single detector, if you use a single detector, okay, along the y-axis, see, it cannot distinguish between a positive frequency and negative frequency. Okay, so same offset of positive and negative will give you the same signal. So it will not see the sign of the offset. it will give you a signal with corresponding to that frequency. It can be positive frequency, it can be negative frequency. And then it is not acceptable, because in NMR you will have all a mirror image around the middle point or the on resonance frequency. Okay. So that is the thing. So you can see it here, the way that it is rotating anti-clockwise and clockwise. You get you cannot distinguish the frequency. So therefore a single coil cannot distinguish positive and it cannot distinguish positive and negative frequencies. Okay, so you have to find out a way so that you will be able to distinguish it. Okay, so this can be achieved by placing two receiver coils. So one can think that you put a receiver coil along the y-axis. So this is your y-axis, this is your x-axis. So you put two receiver coils, differ by 90 degree. Okay, so this is, so one you are putting here, you have a detector here, you have a detector 2 here. Okay, so they are 90 degree. Okay, so and then you will see that you can distinguish now. You can distinguish the positive and negative frequencies. Okay, so now if you let us see, you have a signal which is offset is positive. Consider offset is positive. Okay, so if the offset is positive, that means it is moving in this direction. Now, so this is your x-axis detector, this is your y-axis. So if it is in the positive direction, that means your magnetization is moving this way. So if this moves this way, you will see there will be a, so initially it will start the x-axis magnetization is, or is x-axis, because your magnetization will come here, so you will not see any signal at the it will come to y-axis, you will not see any magnetic moment in here, so that will be 0, or any detector signal along the x-axis is 0. Now as it is moving this way, so you will see slightly the signal will increase in this detector, and you can see now it is increasing. So it will keep on as it rotates, it will, you can see there will be a harmonic oscillation or a regular feature. Okay, and as that during this thing the magnetization is also decaying by T2 relaxation, so the magnitude will also decrease. So if you now do a Fourier transform, you will get of this signal, you will get a positive frequency and a negative frequency, which will be negative in intensity. For a positive frequency, you will get a positive signal, positive offset, and if negative, you will get a negative offset. Now, if you see the y-axis detector, you will see for both of them will be positive, the same way, because initially it will be the maximum, the signal at the detector, and then it will decay and like it will follow the same path, and you now get both will be seen as a positive. So now if you combine them, if you sum them, you will see, because we are seeing the positive, for a positive offset, you will see that you are getting a positive signal. Similarly, if you do the same way for a negative, you will get a negative. The negative or negative offset will be a positive signal. Okay. So this is the way you can cancel the wrong frequency, and this is called a quadrature detection. Okay, so but see, you will see that actually, in fact, there is no other coil put in the NMR machine. So it is the only one coil which does the thing. So what is the trick? How it is being done? Okay, let us see. So, but I told you earlier that the probe head contains only one coil. This is the one coil where it is the radio frequency pulse is also given, and this is acting as a detector. So how it is does? So the receive from the, so whatever signal you are getting from the receiver coil, okay, it is split into two. So see, there is a signal splitter which is splitted into two, and then there is one can do a 90-degree phase shifter. you see the X and Y, they are differ by a 90 degree. So if you do a 90 degree phase shifter, you are converting a cosine signal into a sine signal. So that is actually effectively done by this 90 degree phase shifter. So you get the original cosine function, and now due to phase shift you get the sine function. Same thing, the previously what we showed you, this is your sine and this is your cosine. Okay, so from the same splitter, and now then you are so both parts are then mixed with the carrier frequency. Okay, now you see that we are bringing the carrier frequency is nothing but the radio frequency, or the radio frequency which field, the radio frequency of the radio frequency field which is used in the pulse, or you can call this as a rotating frame frequency or transmitter frequency. Okay, so that is we call the carrier frequency, and you are mixing them. Mixing means actually you are actually doing the subtraction. So if you do subtract this, so if you subtract this only, what you will see that you will have only the offsets will be only left. Okay, so you are now reduced from megahertz to kilohertz. Okay, so this is the way it is being converted to megahertz to kilohertz, so that your electronics can manage this properly. So now so we have explained how both the transmitter and the receiver system effectively work in the rotating frame. Okay, so the rotating frame was introduced in the transmitter system by having the B1 field rotating around, rotating in the XY plane. That is equivalent to your rotating frame frequency, and the rotating frame was introduced in the receiver system by subtracting the transmitter frequency from the signal. Okay, so what we are doing, actually we are actually measuring the frequency offset. Okay, and your so your zero frequency will be at the middle of the spectrum. Okay, so don't get confused with this zero frequency with your reference, or what we like TMS. TMS 0 is given zero value with respect to this. So with respect to TMS, the your carrier frequency will be different. Okay, so that we adjust later on. Okay, so the carrier frequency is this. So if you remember in the very first lecture, I told that it is easier to not first lecture, maybe during the chemical shift, that it is easier to measure the frequency differences, okay, rather than absolute frequency. So that only we have done. We have now measured the difference of frequencies by subtracting the carrier frequency from the NMR signal. Now let us see that when you record a 1D NMR, so there will be certain data acquisition parameters. Okay, so in 1D spectrum is set with transmitter frequency, which is I told you, which is placed at the central position or very close to it of the spectrum. And all spectra, we call this a spectrum. You will not be measuring only one frequency. A range of frequencies like chemical shift. For proton it is around -10 to +20, carbon 13 from -50 to +250, or in fluorine you will see that more than 1000 ppm, like that. So they will have that is called the spectral width. Okay, now the transmitter frequency is mixed, okay, or which is actually subtracted with the signal that comes from the receiver, that I have already told you. Okay, so the signal measured in the rotating frame and the frequencies will be in the audio frequency, 0 to maybe 0 for the central frequency, and then it will be from hertz to kilohertz. Okay, now suppose if you have a nucleus, okay, which has a spin exactly at the same at the transmitter frequency, we call that as on resonance. It will have 0 frequency, okay, because delta nu will be 0, and it will be appearing at the center of the spectrum. Okay, now when you so this is your reference frequency. Now it is when you can now with respect to your reference in NMR reference, it will have a particular value, delta value or frequency value. Okay, so don't get that confused. Again, I am telling. Okay, so this is with respect to the recording or operation of the NMR instrument, but that is done afterwards. Okay. Now offset frequencies. So when it is on resonance, it will be 0. Now if the offset is positive, you will see those peaks will be coming left side of the spectrum. Whereas if the offset is negative or which are having smaller frequency, they will come in the. So if you have NMR, so you can see, so this will be your transmitter frequency, or you will call that on resonance. On resonance nuclei will come here. Okay, so anything which is having a positive offset, and this side will be negative offset. Okay, but if you, when you put your TMS here with respect, so TMS will now, this is 0 with respect to your while you are recording, but when you make it 0, suppose if it is put at 5 ppm, so it will not be no more 0 with respect to this will have some frequency. Okay, so that don't confuse with that. Okay, now as I told you, so there could be more than one transmitter channel. Okay, there could be more than one transmitter. You see, this kind of situation you need when you record a heteronuclei. Okay, suppose if you want to record a decoupled carbon-13 spectrum, that's why I told that there will be always two channels, okay, or two coils, okay, a inner coil and outer coil. So when you record a proton decoupled carbon-13 spectrum, so use the transmitter one channel, because I told you that decoupled spectrum, your inner coil is tuned to carbon-13 and deuterium. So you use that, tune the inner coil to carbon-13 for recording carbon-13. Okay. Okay. So the resonance or the transmitter frequency will be set for carbon-13 into the inner coil. And then as we will be using a decoupling, so the second transmitter channel, okay, we will use for the proton spectrum, or the center frequency will be of proton resonance. Now we'll see that as I told you, the spectral width. Okay, so how you decide that? It's very important. See, this is one parameter. You will see if you fix the spectral width, many parameters will be automatically fixed. Okay, so that is done by proper choice of dual time. Now let us see what is dual time. Okay, so now what we do actually, when after the pulse is given, the magnetization comes to XY plane. Okay, and then we are monitoring the AC signal. So if the that I told, the magnetization will now process as per the offset. Okay. Okay, so you will see that there will be a alternating signal. Okay, AC current, AC signal that can be a current or voltage. Okay, it is done in the, so this current and voltage will be received by the receiver coil as a function of time. Okay, so now you will not be monitoring continuously. So the signal will be now sampled periodically. Okay, so what will be that period? So the neighboring data points are separated by the, so that tells you that neighboring data points, okay, the time between these two data points is called the dwell time. Okay, so that means it is how frequently you are sampling the signal. Okay, so that decides the dwell time. Okay, so now we'll see what way the dwell time and the spectral width are related. Now you can see that this is a signal. So this is a, if you see, this is a continuous signal, but we will not be recording the continuous one. We will be recording the intensity of the let us say current or voltage at this point, and then again at this point, this point, this point, this point. Okay, so that is, so you can see that the distance or time gap between this and these two points is called the dwell time. Okay, that is only I have shown here this and this. It is called the dual time. Okay. Now, if you see so we cannot choose this arbitrarily, the dual time. Okay, so there is a theorem that is called the Nyquist theorem. It says that at least 2 points per period or per wavelength, okay, at least 2 points per period must be sampled in order to characterize the frequency correctly. Okay, it's very important. So if you want to characterize the frequency, you have to collect at least 2 points per wavelength. Okay, so this is done for this correctly. You can see there are 2 points per period. But if you see in this particular case, you see there are 2 waves. This is one and this is another one. So for this the black points, it is sampling properly. There are 2 points collected, but if you see this one which is having a higher frequency, you see that it is not doing, there is a missing data point here. So you will see in this particular case, you will not get the proper frequency after Fourier transform. I mean to say that. So that's why the dueling time is very important. Okay, because we know that the highest frequency is your spectral width, and if you consider the spectral width in Faj, the dual time, because the dual time must be equal to dw is equal to half 1/2 spectral width. Okay, so this is a mask. So once you fix the spectral width, automatically the machine fixed its dual time. Okay, or if you fix dual time, it will fix the spectral width. Okay, you cannot make them separate. Okay, so it is always recommended. That's why it is always recommended to record the spectrum over a large spectral width to make sure that no signals beyond the normal spectral range are lost. Now, again, the spectral width is related to your pulse duration also. So what is, if you remember that we are giving the radio frequency as a pulse. Okay, so so in the pulse mode, what we are doing, we are giving a pulse for a particular duration. So that is the TP. Okay, so now due to that, so this brief pulse, as I have told you in my earlier classes, that this brief pulse act as it covers a range of frequencies, nu zero plus minus delta nu. This is your nu zero and this is your plus minus delta nu. Okay, and that is inverse of TP, or the pulse duration, and that is coming from the uncertainty principle. So you can, depending on what is your pulse duration or the pulse, your period of the pulse, that delta nu is decided. Or now delta nu is related to your spectral width. Okay, because you have a central frequency, then you will have the right side is your the offset, and left side, and full thing is called the spectral window. Okay, so automatically the spectral window will also be decided by the pulse duration. Okay, but in this case, see, you can selectively do the spectral width. You cannot manage spectral window, spectral width and dual time separately. One is fixed, it will be, but here you have to do it manually. Okay, so if the pulse is very shorter, so you will have a, that is the inverse relationship. So you will have a greater delta nu. Okay, so the spectral window SW cannot be greater than delta nu. Okay, so whatever you are getting due to the uncertainty, it cannot be more than that. Okay, so the spectral window must be less than equal to delta nu, or spectral window must be less than equal to 1 by pulse duration, or pulse duration should be less than equal to 1 by spectral window. This is the very important thing you have to remember. And I have already told you that the B1 field of the pulse must be sufficient. The choice of B1 field should be such that it will be able to cause all sets of nuclei processing within the spectral window should feel the same B effective. And I explained to you what is B effective. Okay, so B effective, it is nothing but the vector addition of the main magnetic field, the reduced magnetic field and the B1. If you remember, that is B reduced square plus B1 square equal to your B effective, if you remember. Okay, so that's why normally this the pulse duration is set to 1/4 spectral width inverse. Okay, so 1/4 of spectral width inverse is actually normally set for pulse duration. Okay, so that only you have to check that when you are giving a pulse duration, whether it is matching with that. Okay, if it is not matching, then you may have to change your B1 field, so that, because if you change the B1 field, so this can be modified. Okay. Now dual time, already I have told you, you have to fix it to the dual time is equal to 1/2 spectral width. Okay. Now what is called the time domain data points. So now you are collecting a FID. Okay. So in FID means you have now you are collecting your signal at various points. So how many total points in a FID is sample? A FID as sample is called the time domain data points. Okay. So how many data points is that sample? Okay, so that is called the TD. So we will use this TD in many time, and this TD is also depends on the dual time. Okay, sorry, this TD depends on the acquisition time. Okay, so how they are related? So acquisition time is that for how long you are collecting the data. So the acquisition time is equal to TD into dual time. Okay. So now for 1D spectra, this acquisition time is set such that the signals have completely decayed. So you will see that the FID should, okay, so they should decay completely. Okay. And then the complete measuring time. So suppose if you want to record a large, if you collect large, if you want to carry large number of scan, the total time should be the number of scans. Okay, and this is RD. I'll tell you a little more about that. And then acquisition time. So RD is nothing but, see, when you are bringing the magnetization into the XY plane, okay, during this acquisition time, it may not be going back to the Z direction. Okay, so until unless it goes back to the Z direction, okay, if you again give a pulse, it will not be fruitful. Okay, so that's why between two pulses you have to give some time. Okay, so one pulse, then you give the next pulse. Between that you have to give a gap. That is called the delay, or that is called the relaxation delay. So during that relaxation delay, your all nuclei here in the XY plane, they will go back to the Z direction, or they will align along the magnetic field before you give the second pulse. And then is one term is called the resolution. It is the ability to distinguish the nearby signals, and it is inversely proportional to acquisition. Okay, if your acquisition time is longer, you get a better resolution. If your acquisition is shorter, you get the resolution will be poor. So all these things are related. Now next important thing is the pre-induction decay. Okay, so once so if you see that intensity of a spectroscopic signal, okay, so as soon as your detector start detecting the signal, it will not be uniform. So as the time goes, you will see that it decays exponentially. It is decaying exponentially, okay, with time. But the most important, although the signal is decaying, the frequencies which consist of this signal, they do not change over the time. That is most important. The frequencies remain constant. Only their magnitudes are decreasing. Okay, so such a pattern is called the pre-induction decay, or it is also called as a time domain spectrum, because here the intensity is changing with time. And this is, we know, this is the exponential decay. It is the result of the effective spin relaxation time T2 star. T2 star is T2 is the T2 relaxation time, and T2 star also considering the inhomogeneity of the magnetic system. Okay, so this is the effective relaxation T2 star, and that actually governs this decay. Okay, so now if this FID, because in a sample you will have many sets of nuclei, and you will have many sets, many different which are having different frequencies. So you will have many sets of nuclei in a sample. They will have different frequencies, and each set having their own T1 and T2. Okay, and then in each set there will be different number of nuclei. Okay, so all these things, if you combine to give this will give a complex digital FID curve consisting of n data points. N data points is that the TD. Okay, okay, so it is for how long you are acquiring the data and what is your dwell time. Okay, so that is governed by that. And again, dwell, so it depends also on your spectral window or spectral window. Okay, the number of scans are it is very simple to understand, because it is how many scans, how many time you are collecting the FID. But that is, it is very important to decide what should be the signal to noise ratio. Okay, so if you the signal to noise ratio for n number of scans equal to signal to noise ratio for one scan into root over ns. Okay, so it depends on the number of scans root over. Okay, suppose if you want to increase the signal to noise ratio to the by 2, you have to take the 2 scans will not do, you have to take 4 scans. I think all of you know that this is a general and common thing in spectroscopy. Okay, so if you want to improve the signal to noise ratio by n times, you have to number of scans should be you have to take it will be, sorry, the signal to noise ratio will improve with root over ns. Okay, but see, if you record 1D proton NMR, the number of scans are okay, you can select anything, you can take 10, you can take 20, but there are many experiments, you will see that you cannot decide. So they will be either multiple of 4, they will be multiple of 8, or they will be multiple of 16, like that. Okay, so those are determined by the phase cycle of an experiment, and you will see that in 2D experiments, you will see in your coming classes that that is what is phase cycle and how it decides how many scans. It cannot be arbitrary. We cannot take odd number of scans. It should be multiple of something. It can be multiple of 4, 8, 16, like that. Okay. And then, as I told you, the relaxation delay. Okay, so time between end of the sampling of the FID and start of the next experiment. So this is the end of your FID first, and then starting the next experiment. Okay, so that is the delay time you have to give, and that is needed for the magnetization to go back to the equilibrium value. And normally that if you use a 90-degree pulse, okay, you have to keep that to 5T1. Okay, and the whole thing from this point, the first FID start to start of the second FID is called the pulse repetition time, or it is the effective time for relaxation given is for the repetition of second of the pulses. Okay, that's why it is called the pulse repetition rate or time for pulse repetition rate. Okay. Now RG is nothing but now your sample will come to receiver and they will be amplified, and what that is also restricted how much it's to be amplified. Okay, the receiver gain has to be set such that the maximum intensity of the FID fills the AGT. There is a condition that if the maximum intensity is not filling the ADC, then probably the smaller signals you may be lost. Okay, so that is a very important thing, and nowadays it is done automatically by the most of the instrument. You give a command RGA, it will do it. Okay, and that will be your receiver gain set. Okay, and then you will have the various pulse length. Now you will be giving pulse, maybe just for proton NMR you will be giving one pulse, but if you want to do a 2D NMR, there will be sequence of pulses in gate up. We'll see some experiments. I'll also tell you how we are using the various pulse lengths. Okay, so this is the duration of the B1 field that is switched on. Okay, so now we know that this precessional frequency about the B1 axis is nothing but omega 1, and it comes in the kilohertz range or smaller. Okay, okay, because B1 is not, see, the main field is in megahertz, whereas this B1 is in the main field, if you consider in terms of Tesla, it is in Tesla, whether this will be millitesla or be milli to micro Tesla. Okay, so they will be very smaller. So the rotational frequency or precessional frequency will be very small. So the flip angle of the pulse alpha is determined not only by the length of the pulse but also by the power level of the amplitude. Okay, so that I have told you, the alpha is depends on the gyromagnetic ratio, and B1 is the amplitude of the B1 or the power of the B1, and TP is the pulse duration. Okay, and we are dividing it by 2 pi so that you will get it in degree. So what you will see that in most of the experiments we will use a pulse less than 90 degree or 90 degree or 180 degree, because this much rotations are required for various experiments in NMR. Okay, so you know, suppose if you want to 90 degree, if you know the B1 strength, this is fixed for a nuclei, so you know what should be your pulse duration. So normally, if you see in machine, you will see mostly the P1 is actually 90 degree, P1 called 90 degree transmitter pulse length, P2 is 180 degree. Again, P3, if you tell it is 90 degree decoupler pulse length. When you do decoupling experiment, specifically carbon 13, we'll see that, and P4 is also decoupler pulse length. Okay, so normally this is in most of the instrument, these are the comments given, the P1, P2, P3 and P4. There are many more. Okay, I've just considered these are very important for us. Now before I end this, I have 2 more slides only. So see, so far what I have told you, that if you record the NMR spectrum with a 90 degree pulse angle, you get the most intense signal, because all the magnetization come to the Y prime axis and your detector is there. Okay, okay, so if you want to do a single experiment, then this is the best. You brought all the magnetization to the XY plane and detected. But suppose if you want to do a large number of scans, then as I told you, if you give a 90 degree pulse, before you give the second 90 degree pulse, you have to wait for minimum of 5 T1. Okay. So, and sometime you will see that T1 varies from millisecond to second. Suppose if your T1 is 10 seconds, then you have to wait for 50 seconds if you give the next pulse. Okay, so that is a lot of time. So if you want to do a large number of scans, that will take a longer time. So what Ars said, that you need not to give always 90 degree pulse to get the best spectra or signal to noise ratio. Okay, so the Ernst angle is the flip angle for excitation, okay, of a particular spin that gives the maximum signal intensity in the least amount of time when signal averaging over many transients. That means if you are recording in a longer time, it is better to use the Ernst angle. Okay, now we'll tell what is Ernst angle. Okay, so now if you see that if you flip the magnetization by alpha, okay, this is called the flip angle of the pulse, you can see that the magnitude of the Y component magnetization is M0 sin alpha, and Z component is M0 cos alpha. Okay, okay, so that is only I have shown here. Okay, now, so if you see the how much reduction is happening in the Z component. Okay, so Z component normal it was M0, but now current after the pulse given, the value is m0 cos alpha. So this has been the reduced. This is the reduced amount. Okay. So this much is reduced. So if you, that means before you give the next pulse, this reduced amount has to be recovered. m0 minus m0 cos alpha has to be recovered. Or you can write m0 into 1 minus cos alpha. Okay. This has to be recovered. Now let us see. Okay, so that we have seen the maximum signal result from a 90-degree pulse. Okay, so that 90-degree pulse bring everything here. Why? And you detect the signal. Okay, now as I told you that for a 90-degree pulse, the delay should be 5 times of T1. Okay, so that the Z component magnetization recovers by more than 95% before the next pulse to avoid saturation in a multi-second experiment. Okay, so but if we use a smaller flip angle, okay, so let us say alpha is equal to 30 to 50 degree, then you will see that sine alpha is greater than 1 minus cos alpha. That is very important. That means with a small flip angle, you are getting more magnetization in the y-axis. Okay, that means you are detecting more signal, and your system goes back quickly to the Z direction. So what Arns said that the optimal pulse angle should be cos alpha is equal to exponential to minus TR by T1. TR is the, I told you in the previous, if you remember, that was the pulse repetition time, between the time gap between the two pulses, and what is the T1 of the speed. Okay, so or this TR is the acquisition time plus the relaxation delay. So if you know the T1, okay, and you know the what is the pulse repetition rate, you can choose the what should be the optimum alpha value you should choose, or and that will decide your TP, because TP is related to the alpha. TP is directly related to the angle or pulse angle. So, or if you know if you have a fixed alpha, you can find out what should be the repetition rate. Okay, but because T1 you cannot change. So this is the summary how one acquires a 1D spectra. Okay, so first thing is that suppose you are going to the going for the recording a spectra, you must see whether you may want to record a phosphorus NMR, but your probe head is in proton NMR, so you have to change the probe head. If you change the probe head, you have to tune the probe head. Okay, and then you have to do the calibration of the pulse length. Okay, we will see how to do that later on. But okay, so but if let us say you want to, the probe is already in proton and you want to record proton NMR, then these three things are not to be done. And then the setting the correct temperature for the measurement. Then you start from here. Okay, you set the correct temperature for the measurement. So sometimes you want to do a room temperature, high temperature. Depends on what sample, what is your purpose. And then you position the NMR sample tube into the spinner and then insert the sample into the magnet. I have told you that spinner turbine, you have to put the sample and then insert. Okay, and then what you do, there are already stored SIM values. Okay, that is stored in the computer. To call that, otherwise it will be very difficult to do. Already it is there. Okay, for that particular probe head, and then you do the fine tunings, okay, by changing the values. Okay, and then you activate the field frequency. You have to lock the sample and optimize the log, then adjust the field homogeneity using by simming, the room temperature simming. Okay, you first do the axis and then the out of the axis sims. Okay, and then determination of the receiver gain, that can be done by automatically. You give a command, computer will do automatically what should be the receiver gain. Okay, and then you take a preliminary scan with a large spectral window, let us say 20 ppm or 30 ppm. Okay, and then you see till how long your peaks are there, and then you decide your final spectrum, final spectrum with sufficient signal to noise ratio and optimized spectral width. So that once you decide that, and then you record how long you want to record it. So that will be decided by the what signal to noise ratio you are looking for. Okay, so if you have any doubt, you can ask me. So I'll stop here. If you have any doubt, you can ask me. Anybody has any doubt? Any question, anything you can ask, or you can type your query. So I'll continue with this another 2-3 classes. Okay, then my part will be the module 1 will be over, and then you will be learning about the 2D NMR and other things. Okay, so these are the things I'm telling that these things will be coming when you are learning the 2D NMR, and all these things will come. Okay. So next class I will tell about the relaxation, mostly the relaxations, very important, and then we'll go for decoupling and also dipolar coupling. These are the 3 important things you have to know before you want to learn the 2D NMR. So I'll try to finish maybe 2 or 3 lectures, 3 lectures I need. Okay, any doubt? Or any queries or any suggestion? And what is about you? I should know what way you are feeling about the course. See, you all are individually sitting. I am also individually sitting here and speaking. No interaction. I think. Okay, then I'll stop here. If you have any queries, you can send email to me. Okay, or you can ask me in the next class. Okay, so I'll stop here. Thank you.